Alright, hi you guys. Today we'll be talking about the first part of applications with vectors and just some helpful hints of working with vectors and physics. Okay. Number one, draw a picture of what is happening with the forces upon the object. Simple as that. If you draw a picture, it makes your job a whole lot easier. Okay. Also, part two is label what you know and don't know. So if you know a certain force is acting a certain direction, label it. And then also label what you don't know in the picture. It just helps out. It helps with the visualization of the whole problem. Okay. My strong suggestion, like I've said before, is try to use the tail to tip method to draw the resultant vector. Okay. And also, most important, use the windrows to see the correct direction to go. So every time you start a new, if you're doing the tail to tip method, make sure you are drawing the windrows at the tip of the last vector that you're working with. Okay, and one more thing. Remember that work is force times distance, which in this case will be the dot product of the two vectors that we're working with. Okay, so for this first one, a force is acting due north on an object at 150 newtons, and another force is acting on the same object due east with 90 newtons of force. What is the resultant vector of the force upon the object, and we'll also find the direction to help you out with that. Okay, so right here I've drawn the two vectors, or the two forces, the 150 newtons straight up, the 90 newtons to the right. Okay, it's due east. Okay, so that's drawing my picture. Labeling what I know and what I don't know. I make sure I label it 150 and 90 newtons just so that I keep track of both my units and my numbers. Okay, and I'm using the tail to tip method to just really help out. Okay, alright, and the windrows is, well, this one's pretty easy because it's due east. So that's pretty easy. It's just straight to the right. Okay. Now the cool thing is that when I'm doing this, I'm actually creating a right triangle. So for those of you guys thinking at home, can I use good old fashioned Pythagorean theorem? And when you can, you might as well. So yes, you can use good old fashioned Pythagorean theorem. And this is actually, let me consult my notes, 174.9 newtons. Okay, and that's that resultant vector right there. Now, if you also, as a bonus, if you wanted to get the direction of it and which way it's acting, you would want to find the angle here. Okay. All right. So now, obviously, we're going to be using a little bit of trig. So this is going to be a tangent of theta, and we'll call this theta just for the heck of it. Alt 233. Okay, and if you remember from last semester, theta is Alt 233, and this is going to be 90 divided by 150. Okay, and then we're going to find out that theta is going to be the, well, let's just go ahead and use good old arctan. All right, arctan of 90 divided by 150. And that is going to be 30.96 degrees. Okay. All right. And so that angle is going to be right there. Now, how do I tell that direction in terms of force and everything? Well, if you notice, I'm to the right of due north. So I could say this is east of north, or this is the way to actually write it. It's really interesting. North 30.96 east. It's weird, I know, but that's just some ways that some cartographers actually write with directions and stuff. So you actually reverse the two, the east of north and the north of east. It's just weird how it works. I don't know why it does it that way. I should probably look it up, check it out, but right now I'm just trying to teach applications of vectors. Okay. All right, let's go to the next slide. Okay, so someone is delivering a 125-pound package up a 20-degree incline ramp that is 15 feet long. Okay, first off, that's a ridiculous incline, but I just picked it for this problem. Okay, find the work done by gravity. All right, so here's my ramp. It's 15 feet long, 125 pounds, and my work is going to be force times distance. So this is going to be pounds feet. That's what we're going to represent it as. Okay, now since this is gravity, gravity never has any good representation. So we're going to label it as negative. Okay, Now this force is going straight down. So this force is going to be represented by the vector, and we will use vectors for this. 0, since it's not going forward at all, negative 125 right there. Oops, let's get the right thing right there. Okay, now distance as a vector is going to be represented as xi plus yj. Okay, now if you remember, these are the unit vectors right here, and you could almost say that this was 0x minus 125j. Okay, so those unit vectors would work right there. Okay, now since I know some stuff right here, I can actually figure out what these two horizontal and vertical components are going to be. So sine of, what was it, 20 degrees? 20 degrees is going to be equal to x divided by 15. Oops, nope. That would be y divided by 15. Okay. And cosine of 20 degrees is going to be x divided by 15. Okay, now why do I look at it that way? Well, I know that this is the 20 degrees mark. Okay. All right, I know this is 15 feet right here, so I'm going to use right triangle trigonometry to actually figure out these two parts. This is going to be the x, and this is going to be the y, so I might as well figure those out. Okay, so let me do some calculations real fast. All right, so I've set it up. I've just multiplied both of them by 15, and I got 5.13 feet and 14.10 feet. So I'm going to represent distance as 5.13 I plus 14.10 J. Okay. And obviously if you represent as a unit vector, you don't need to put in the actual parts. Okay, so now when I do the dot product, it's going to be work equals parentheses 0 times 5.13, which makes sense because I'm not really doing any work over a horizontal distance. There's no force. It's just pulling down. Plus, what is that? Negative 125 times 14.1. Okay. Wait, I just realized I mixed those two up. Holy schnickies. Yep. Yeah, I'm going to go back. These two should be reversed. I just realized that. So that should be 14.10 plus negative 125 times 5.13. Okay, and if you remember, I had them just mixed up here, so just reverse those two. Okay, and so since the first one's just going to be 0, I'm just going to go negative 125 times 5.13, and that's going to be negative 641.25 foot-pounds. And yes, that sounds weird unless you are actually working in physics, but then you're like, oh yeah, foot-pounds, I know those. For those of you guys not in physics, sorry. It's just weird how it works that way. Okay, so once again, just reverse these two. I made a mistake when I put them in. So this should be 14.10 I, and this one should be 5.13 J. Okay. Alright, now on to the next problem. Suppose there is a 100-pound sign hanging in front of a comic store. The two braces make a 35-degree angle where they support the sign. One of the braces is parallel with the ground. What are the magnitudes of the force exerted by the support bars? Okay, so let's draw this out and label our known and unknown. Okay, so I'm just pretending that this is the side of the store. It doesn't matter how high up it goes. It kind of looks like a flagpole in Mario Brothers. Sorry about that. Okay, so they make a 35-degree angle. I made one of them parallel. Now, obviously, if I switched one of them down, it would still be exerting the same force. Well, it would be a little bit more. No, I think it should be the same. Okay, so here's the sign. It's 100 pounds, so that's the force being acted down. Okay, and then here's the 35-degree angle. Now, here's the cool thing about these type of problems is that I can draw something parallel with it to go down to here, and I would have another 35-degree angle. Now without this, this problem is going to be really hard unless you draw this second part. Okay? But you can say that this force is enacting upon this sign, holding in place, and this force right here is being held by this. So there's a horizontal force, okay, and there is this angled force at 35 degrees. Now, obviously the vertical force is 100 pounds, so we already know that. It's like knowing the result, the actual vertical component, and all you need is the resultant and the horizontal. But in this case, we're just wanting to know these two parts. Okay, so what we need to do is just set this up. So this would be sine of 35 degrees is equal to 100 over, let's call that force 1. Okay, and we'll say this is force 1, the first bar. And then we'll say this second one is the second force right there. Okay. Alright, and then the other one is going to be, let's see, tangent of 35 is going to be equal to 100 divided by force 2. Okay, now obviously if we switch them up, force 1 is equal to 100 divided by, now if you're using a TI calculator, please put this in parentheses, otherwise they're notorious for not putting those exactly in parentheses. Okay, which is going to be 100 divided by tangent of 35. Okay, and let me do my calculations really fast. Okay, so our calculations result in this first bar is it is exerting a force of 174.3 pounds upon the sign, and the second force, the parallel bar with the ground, is exerting a force of 142.81 pounds. Okay, now that's really interesting to see that, but this is probably good for you guys who are going to be a structural engineer, or for those of you guys just looking for common sense. The angled one is always probably going to be a little bit more than the one parallel with the ground, that you need to be stronger and stuff. Okay, all right, that's it for part 1 of applications of vectors. I'll see you next time in part 2.